In this screencast, I'm going to show you how to calculate an equivalent length for minor head loss. This length is the length of straight pipe that would cause the same amount of head loss as the total minor head loss. So let's consider a galvanized iron pipe. It has a diameter that's equal to 0.075 meters, and it has a 90-degree threaded elbow. And what we want to know is what is the equivalent length. And how would this change? Instead of having a 90-degree threaded elbow, we have a flanged elbow. What is the corresponding equivalent length for this? And for this problem, we're going to assume that the flow is wholly turbulent. So we'll start with the equation for equivalent length. So the equivalent length is equal to K sub L, which is the loss coefficient, times the diameter of the pipe divided by the friction factor. And this K sub L is the loss coefficient, and it depends on the geometry. So we'll start with K sub L. These values are tabulated in any fluid mechanics book. And here, when we look them up, we find that it is equal to 1.5 for the threaded elbow and 0.3 for the flanged elbow. One thing to keep in mind, these loss coefficients are not material dependent. So we could have a copper pipe instead of an iron pipe, and we'd have the same two loss coefficients. So how do we find the friction factor? So the friction factor we're going to have to get from the Moody chart. And in order to use the Moody chart, we're going to need to know the Reynolds number and the roughness factor divided by the diameter. The first thing is this Reynolds number. Because our flow is wholly turbulent, we don't need a Reynolds number. We can just use the line in the Moody chart for wholly turbulent. Here, we're going to have to look up the roughness factor, and that's where the material does matter. So we have a galvanized iron pipe, so we go and we look up the roughness factor for that, and that's going to be equal to 0.15, and this is where you have to be careful. The roughness factor is given in millimeters, not meters, but everything else is in meters. So make sure that you use the correct order of magnitude. So now let's calculate our epsilon, roughness factor, divided by D. So this is equal to 0.15 times 10 to the minus 3 meters. And our diameter, go back to our problem, is given right here. And so we divide that by 0.075 meters. And so we find that this ratio of roughness factor to diameter is equal to 0.002. So with this number and the fact that it's wholly turbulent, let's go to the Moody chart and figure out what our friction factor is. So again, we know that our epsilon over D, roughness factor over diameter, was calculated to be 0.002. So that's right there. And we're looking for where it intersects the wholly turbulent flow line, which is right there. And if we do a straight line across to the friction factor over here, we find that the friction factor is equal to 0.023. So let's go back and put that into our equation. We'll start with the threaded elbow. So that equivalent length is equal to our loss coefficient, which is 1.5, times our diameter, which is 0.075 meters, divided by the friction factor of 0.023, and our equivalent length for a threaded elbow is equal to 4.9 meters. We do the same thing for the flanged elbow. The only thing that changes is our loss coefficient. So our diameter stays the same, as does the friction factor. And when we calculate that equivalent length, that's going to be equal to 0.98 meters. As expected, this is considerably lower than the threaded elbow, but certainly significant. So this problem had only one fitting, but equivalent length can be calculated for many fittings by calculating that equivalent length for each one and summing them up to get the total length.